All right. Well, let's get started. Okay, so sorry, what part of the entanglement? So we're doing revision.
Yeah.
Yeah.
I have questions about the Bell's inequality.
Ah, okay.
Page
Bell's inequality. Okay, so starting here.
Yeah.
And yes, this thing. And quantum case. And we evaluated that thing.
Yeah.
Yeah. Which slide?
I'm wondering what's the observable matrix?
What does the observable here mean?
Yeah.
Yeah. Well, as usual, the observable means, so the, yeah, we've got two types of observables for each party, Alice and Bob. And so really what it actually comes down to is, again, just some measurement that each box makes in a particular basis. So when I say you measure this observable Z, then what that really means is, yeah, to perform a basis measurement, 0, 1 basis. And X means that if the observable is X, then measure in this plus minus basis. So like what these knobs are doing is basically to change the basis of the measurement that you're doing. So these ones may look a little bit unfamiliar because we've done this a lot of times, but we never did this one. These ones are also basically the same idea, except that the basis that you're measuring in, say for B, is a state like 5 pi over 4, and this angle, what I mean by the angle, it's basically I'm talking about the Bloch sphere. So when I say, it's a bit wonky today, so here is X, Y, Z, and here's the state plus, here's the state 0, down here is minus, and over here is, sorry, it's state 1, state minus, and the angle that I'm talking about here, so I've defined the state theta, and this is actually just, so the 0, 1 basis would correspond to an angle of just theta equals 0, because theta equals 0, because then this theta state is actually just the same as 0 state, and then I also need the state which is conjugate to that. So the 1 state would be theta equals pi over 2. Sorry, pi, I think. Yeah, pi. So in other words, basically this state here, which is straight up, and this state here straight down. The plus state, this basis of plus minus basis, this actually corresponds to theta equals to pi over 2, because in general, so we're actually just in this ZX plane here, right? So it's a bit badly drawn, but basically this angle theta is this angle in the ZX plane. And so the plus state is the angle pi over 2, and the minus state, well, you could do 3 pi over 2 or minus pi over 2. And these two measurements on B are actually just some angles that are sort of in between those two. And for Yeah, so these ones in this case, so this first observable, which is z, b is minus z plus x over root 2. So this would correspond to an angle of pi over 4, and so that's that term there, or 5 pi over 4. So it'll be like this one, or the one that's pointing the reverse direction. So this is pi over 4, this is 5 pi over 4. And here, the other b one, I'm calling b dash, which was z minus x. So this is 3 pi over 4 and 7 pi over 4. Right? Yeah. And which one you call the minus one is, it just depends upon the, well, in this case, the minus one was the pi over 4 one, mainly because there's this minus sign here actually. So you can work through it so that you work out this is the state that you have with the minus, and this is the state that you assign a plus to. Yeah. Does that make sense?
So, to my understanding, that the matrix A or B is just a measurement matrix, which consists of a set of autocoded
Yeah.
zero state or one state.
Yep. Yeah.
So that matrix is actually the outer product of 0 minus the outer product of 1. Right.
Which one? This A?
Yeah.
Yeah. So A, when we measure in the 0, 1 phases, this would so this is just equal to z, right? And this one is equal to that matrix, or if you like, you can write it in matrix form. So this is the way that we normally write it: 1 minus 1, 1n minus 1 on the diagonals, and yeah, and so that's how we would write the observable matrix, because you remember, if we go back to the lecture on the observable matrix, then basically the observable matrix is always written as something like, I forget my notation actually. I forgot my notation, but I hope you can cope. But essentially it's called sum over n. So there's a bunch of states where you perform your measurement in. So these n's are all the measurement bases. So in this case, it's 0, 1, or plus minus, or this state with pi over 4, 5 pi 4, so forth. And then these are just some values that you assign to each outcome, because remember, any observable is really just, you just make a measurement and then you probabilistically getting some values, this and that. And then when you say you want to make an average, what you just do is you say, okay, so I've got that probability, P, got that probability Q, and then you sort of add them up with the value times by the probability. So eventually when you do the expectation value, what you're actually in the end doing, you're just doing the usual type of averaging, where you've got these values, same numbers here, and then multiplied by the probability that they occur with, right? And this operator is just a convenient construction such that whenever you want to evaluate this average, I mean, this is more or less the definition, if you like, of an average, but then this is also equal to that, and by defining the operator in this way, we can just do a kind of a convenient calculation like this, and it'll always reduce to the real definition, which is just summing over some values over a probability. And of course, with the density matrix, we also have that. Yeah, so in this case, the observable matrix is, so the outer product of these outcomes, and then the value is just plus or minus 1. And we do this plus or minus 1 values because originally when we were talking about the classical case, that's the setup that we had. So when CHSH, these 4 guys, when they derived this inequality, that's the setup that they defined. So they said, okay, we've got some boxes, and there's 2 settings. Basically means there's 2 observables, and this box just outputs either 1 or minus 1. Right? Those are the values that you're assigning. And then just according to what probability they occur with, that's determined by, well, say these particles that are going in, and also whatever the rule that this box contains in order to assign plus or minus 1. So, it might be simple formula like, okay, so if it's blue, then it's minus 1. If it's red, it's plus 1. It could be as simple as that, or it could be something more complicated than that. But, it's an arbitrary rule. But in the quantum mechanical context, we have, I would say nearly the same thing, but it's actually not quite exactly the same. So it's the same in the sense that, okay, so this thing also only reads out plus or minus 1. So that's exactly the same. It's the same in the sense that this thing has just 2 settings. So you can just switch between observable A or A dash, or B and B dash. And so that's the same. So really the only difference is in this particle that is going between them, the thing that is producing the correlations in the first place. So in this case, that's the thing that will eventually break this bound, because this doesn't sort of anticipate that it's possible to have observables which are kind of locally based, right? So A times B looks like it's completely local, right? Because A is at A and B is at B. But somehow, even though they perform their measurement locally, because of entanglement, it's not really actually local. So it's not. So somehow measuring on Alice really does sort of affect Bob somehow. And then there's sort of more correlations in this quantum mechanical case than there is classically.
How can we determine the matrix P? So YP is equal to
why is it these things? Yeah. So that I didn't tell you because it's a little bit, it's just tedious. So you can choose B and B dash with some other values. That's no problem at all. The only thing that would change is that this final value will not be this big. So, for example, I think if you just chose, say, A, Z to be these two, and then say B, B dash to be like also Z and X, I think I'd have to check to do the calculation, but my guess is that I think you'd get exactly 2. And so that is, it doesn't show the most quantum kind of behavior, because what we're the interesting thing about this is that we've derived what we thought was a universal inequality, right? So the inequality is that it's less than 2, right? We derived what we thought was something that should be true in any situation, any variables, any particles, very few assumptions. This was supposed to be almost like a law of nature, right? But somehow quantum mechanics does break it, and the situation when it breaks it the most is the case that I'm saying. So if you choose these observables and you have this entangled state, in that situation, then this can be like 2√2, which is bigger than 2, right? In other situations, it could be less than. It would probably be less than that. This is sort of the optimal case that, and I didn't show you why this is optimal or how you can work out it's optimal. I mean, it's not so hard to work out probably what the optimal case is. Probably what you'd do is you'd first start with something a bit more general, right? So firstly you'd say, okay, well, what if I did a more general measurement of A prime, B prime, right? So I could just start with 4 angles, like theta. So I could have a theta 1, theta 2, theta 3, theta 4. And then for that 4-dimensional parameter space, make some plot, and then work out this thing for every single theta 1, theta 2, theta 3, theta 4, and then look at that graph in this multi-dimensional space, and then say, oh, okay, so it looks like it's a maximum here and here, and then to save you all that trouble, I've already given you the answer.
So we can arbitrarily choose a measurement. Yes.
But it's just that this particular case is the most interesting because it's the one that actually breaks this CHSH inequality. Yeah.
Then can you show us how to compute the expectation value of AB?
Okay. Like this calculation? Yeah. Okay. Sure. Okay. So probably the easiest way. So here we've got our state, which is 1/√2, 0, 0 plus 1, 1. That's the state. And we can do the first one. So let's try and calculate AB. So let's substitute the definitions of AB. So this is, I'm going to put an A here. ZB plus XB. There's a minus sign here. Pull that out. There's also a factor of 1/√2. Okay. So I just substituted the definitions into there. So as usual, I've omitted tensor product of these things. What I mean by that product is that it's tensor product, so that this is originally a 2x2 matrix, but tensor product of these two make it a 4x4 matrix. And it should be, because eventually we're going to use this vector in a 4-dimensional space. And so I could do this in a few ways. I could sort of find what this matrix is and then do it sort of with matrix algebra. I think what's easiest actually in fact is to just so use the fact that if you have a sum of matrices and then you take the average of that sum, it's the same as the sum of the averages. So what I mean is so the sum of so this matrix, you add them, take the average, is the same as if you take the average of these two individually. Okay, so let's just work out what this first term here is. So ZA, ZB. So we can take the expectation value in the usual way, just using our expectation value formula. And then, so we can substitute the definition. So over here, this goes in twice. So there's a factor of 2 of these 1/√2s, and these things are bras as usual. Like this. Okay. And then, so we can operate these z's on 0. And so, as usual, z on 0 produces 0, z on 1 produces minus of 1 state. Okay, 0 plus 1. So, z applied on 0 just gives 0, z applied on the second 0. So basically this z is applied on the first one, this z is applied on the second one. So this one is unchanged. This one applied on this one produces a -1, but this one applied on that also produces a -1. So there'd be -1 squared. Of course, that's just 1. And now we can just take the inner products between these two states. So only the same states will give non-zero results. So that one and that one gives 1, and that one and that one gives 1. So this is 1. Okay. So that's 1. So now let's do the second term. So ZAXB. Okay, so we substitute in the state. And forgot this one. Okay, so now we apply this operator. ZA on 0, 0 produces just 0, 0, but X flips the 0, right? So this will become 0, 1. This one, ZA on 1 will produce a minus sign, and then X will flip it, and it'll be this. Okay, now we take the inner product. These have nothing in common actually, so there's no 0, 0s over here, there's no 1, 1s. So actually this is 0. And so So combining those two, we should get minus 1/2. So I think that's right. Yeah, okay. So this one has a minus sign.
I remember that in homework 9 we actually used another method, which is rewrites the composite in another basis.
Right. Yeah, I think I did that because that was sort of from our previous version of the course where I didn't actually teach the Bell inequality, where I just had this Bell inequality thing in homework, and I think all the class knew at that point was just how to perform averaging with probabilities and things like that. So I think I just framed the question in that way. Of course, that's totally correct too, but maybe, for you guys who have now learned a few more tricks, this might be faster. But of course, if you did an experiment, then it'll be closer to doing maybe what I did in homework, because you only get probabilities, and then you calculate anything from sort of first principles from the definition of an average. Okay. All right. So next.
Another question.
So Elin has quite a lot of questions.
Yeah.
So Danny, you can ask any questions if you have. Okay, all right. Okay. What?
Can you explain the local relativity?
Oh, still in this one. Yeah. Yeah. Yeah, it's a tricky one to explain. But it comes down to basically what I was just already saying a couple of moments ago. So what I'm just sort of trying to get across here, and I'm not sure if, I don't know if I can really completely do it, but just to give you an idea of what the significance of this is basically what I'm trying to convey. So, as I said, this original CHSH is really purely a statement of probabilities, right? And with some key assumptions, it should be a completely general statement about any kind of probabilities of independently measured systems, right? Because these people are far away from each other. They can't really communicate except for like looking at statistics of some kind of common source. But apart from that, they can't really, communicate to each other at all. And they have a rather limited kind of measurement device in the sense that it only outputs ones or minus ones, and it only has two settings, right? So it's kind of a rather limited situation. But within those assumptions, it should be completely general, right? Like you don't have to say anything about what kind of probabilities these particles should obey, or really anything about what the rule is for when this blue ball goes in, you know, what happens inside this box, you know, what is the rule that outputs this -1, you know, perhaps it's even like, you know, it's very complicated, it sees a blue ball, then it, you know, puts it into a very complicated formula, flips a coin, you know, does all kinds of strange calculations, and then it goes, okay, -1, right? It could be extremely complicated, but it's completely arbitrary. Right? But so it's kind of, you know, it's a specific situation, but again, it's still, you know, quite general because there's a lot of degrees of freedom that could be changed, right? So the key thing is, well, we derived what we thought was this very general inequality, but then, well, apparently something breaks down. So apparently some assumption has broken down, right? And then so you have to think, well, what assumption broke down there? Because, you know, I just got an answer which is violating this inequality, right? So basically what it comes down to, the way that people phrase it these days is that it's this idea that well, you know, if you observe something, it's only dependent upon something which you are sort of looking at, and you know, there's no opportunity for something like a faraway alien to be controlling, you know, what you're seeing, right? Like what you think is there should be purely dictated about by what you are seeing there, and not some mysterious forces from far away. So I think that's sort of the idea of local realism, that when Alice makes this measurement outcome of, say, this blue ball going in, it's only dependent upon the blue ball and nothing got to do with, say, what Bob's doing on the other side of the planet or the universe. So basically, because of this entanglement, when you have entanglement, remember, so I think I started this lecture set and said that, well, so actually there's this sort of effect that when you start with this entangled state, right, there's this special property that entangled states have, which is that this state, like 0011, is actually mathematically completely equivalent to the state like plus plus state plus minus minus. And so basically what that means is that, say Alice does a measurement first, then that actually kind of influences what Bob gets, because if Alice measures in the plus minus basis, then Bob will only get a state which is either plus or minus. But if Alice measures in the 0-1 basis, then Bob will only get 0 and 1. And, you know, 0 and 1, okay, yes, it's random, but they're definitely different states to plus minus, right? So, yes, you get some random mixture, yes, but it's definitely not the same thing. Well, it shouldn't be the same thing as plus minus. So somehow it does appear, when you do this kind of argument, that that Bob's state is actually influenced, right? But it's a bit subtle, because it's actually hard to sort of see this effect. So you might think, okay, well, that's, you know, already clear, you know, that something, Alice is influencing Bob, you know, I've written it down. The subtlety is that it's actually still not possible to really make a conclusive measurement, or conclusive. Bob actually still can't really tell whether it was 0, 1 or plus minus, because in either case, he either gets this state which is like, so if Alice measures plus, so if Alice measures 0, 1 basis, right? Then basically what Bob will get, say, just, if they repeat the measurement many times, is, a bunch of states which are like a mixture of ones and zeros, right? And then we can use what we learned actually in the last lecture, which is that a mixed state of such an ensemble would be actually the state which is like that, because it's like 50-50 the density matrix 0, 0, 50-50 density matrix 1. But if Alice measures in the plus minus basis, then Bob definitely gets a bunch of different states, like so forth. But this time the state would be 50-50 plus states and 50-50 minus. But actually the density matrix is actually exactly the same. And it's because these are like completely mixed states. And so if the density matrix is the same, then any kind of observable that you want to make, so say you did some observable like here, right? It would be exactly the same either one. So just using this isn't quite enough to tell the difference of what just happened between here and here. So it gets very close to looking like, like there's this so-called spooky action at a distance, but it's not quite there. So you need something a little bit more subtle than just taking the expectation value. And then so that's what this CHSH thing does. And, this is an example where this sort of kind of subtle correlation actually comes up and shows that something a little bit more than classical is happening, because it breaks this CHSH inequality. I think I'm not really gonna ask you in the exam to write an essay on local realism, but I think it's just interesting. Well, to try and understand like what is the source of the the contradiction basically, right? Because on one hand you derive some inequality which supposedly should be totally general, but then now we've just broken it. So what went wrong? And so what people say is that basically local realism broke down, and it's basically because this entangled state here, does have some kind of correlations which are just impossible in classical physics. Okay. Next question, Danny, do you want to?
Yes.
Yep.
I have some question about the composite systems.
Okay, let me open that up.
I wonder if should we just go through it or
Okay.
about the measurements specifically?
Measurements, right? Okay, so, well, all right, so let's just quickly recap it so that you can just stop me at the parts that are confusing. So, yeah, so for basically, if you've got two systems, then the idea is that the total wave function can arise from, you know, all possible combinations of the states that are on a single system. So if you had a single system with D levels, so here I've got an example with 3 levels, right? So each single system has 3 levels. And so with a 3-level system, and if both Alice and Bob, so the second one is Bob, first one is Alice, they have a 3-level system, then there's of course 9 different combinations, and so the wave function can be in an arbitrary superposition of any of these 9 states. And so this was an example of independent states. So so if you start with that particular kind of general setting, then some classes of states where these quantum states are, say, completely independent to each other, have a special form, right? And the special form that this has are these independent states where you have this kind of product form. And so instead of having the arbitrary coefficients, so for example, over here, this was like 9 completely independent coefficients. Whereas over here, there are less degrees of freedom because this has to be a product form, and that product form is not as general as 9 independent coefficients here. This actually only has 6 complex degrees of freedom. And when you do a measurement on this kind of system, the most general measurement you can actually make is just it's the same idea as normal. So for example, we've got these nine states here, and so you could make a measurement in any kind of set of states which are orthogonal here. So, well, I'll give a couple of examples. So say like 2 qubits, say we've got 2 qubits like this. Each one of the qubits, say this is Alice's one. And here are Bob's states. Okay, so one possible basis that you could have for 2 qubits is just this tensor product, and again all 4 combinations of these states, which I normally write as something like 0, 0, 0, 1, 1, 0, 1, 1, just to be a bit more compact. But and so the wave function of this 2 qubit system would in general be written something like this, right? 0, 1, 1, 0, 1, 1, right? So that would be completely general wave function of the 2 qubit system. But this is just one basis that I could just choose to write. And just like for qubits, I could have started with some basis like, you know, I could have also used some other basis, plus minus basis, for each of them, or actually any basis. I could equally write this 2-qubit wave function also in any basis. So in this case, this would look something different, you know, plus plus, plus minus, minus plus, minus minus, like this. So I could write that same 2-qubit wave function also like this. But actually, I don't even have to limit myself to states, this basis states that are that look a bit like the single qubit one. I could even write some wave function in some entangled basis. So I could say define states like so I've written plus minus, so there's 2 here, 2 here. So actually, this is also a basis. It's just so happens that the basis itself is entangled, but I can still, you know, write my 2-qubit system also in terms of these 4 and you know, so whatever, like C, so this would be plus, 0, 1, I don't know, minus, and then, so there's always like 4, right? So there's always four basis states because, you know, you can sort of think of it like, so in the qubit case, like you can think of the basis states sort of just as 2 axes, and then all these other states are some other kind of rotations of these axes, right? So that when you view your vector, it's, you know, it looks different because your coordinates are different, right? So in the qubit case, you could kind of visualize it, but okay, so for 2 qubits, then you have to think of 4-dimensional space, and then actually all these, you know, coefficients are complex, so you can't really literally visualize it, but the point is basically the same, which is that, you know, that's one kind of basis choice. Here's another basis choice. Actually, this is another basis choice. There's many different basis choices I can make, right? And so when you make a measurement, and when you make a measurement on this composite system, you can also choose, you know, what basis to measure in, and then the rule for the measurement is still the same, right? The same as what we always do. So if we started with this state and we're going to choose this as our measurement basis, then we would get, for this measurement of the composite system, just probabilities according to the usual rules. So say we get this outcome, and the probability of that would be A00 squared. And the probability of this one would be A01's modulus squared, right? So that's if we did the measurement in the 0-1 basis. But if I did it in the plus-minus basis, of course I'd get some other probabilities. It'd be like B0 squared. Or I can even make a measurement in this entangled basis, and then I get probabilities of C0 squared and so forth. So that's basically all I'm saying there, that the rule is always just the same. So in the composite system, you can still just write down your probabilities in the usual way. But what we often do, and this is kind of more physically motivated because these are like separate particles, kind of often the more common case that you encounter is that each of these particles are measured by a separate box, right? And if they're measured by separate boxes, then you normally don't get this situation that I was talking about here, because this is, you would need some kind of rather complicated measuring device to achieve this, whereas this one, it just means each particle goes in each box, and then each box you measure in some basis, so it might be 0, 1, might be plus minus, might be something else. And then in this case, the 4 outcomes that you get 4 outcomes because even though each box only outputs two outcomes, you still get 4 outcomes because basically 2 times 2 is 4. So you get 4 outcomes according to 4 combinations of whatever you get in the first box and whatever you get in the second box. So you get like S0, 0. So this is like the outcome 0 for both of the boxes, or 0, 1, or 1, 0, and so forth. And then the rule for working out probabilities are the same. The modulus squared. And then this is just saying the same thing now in terms of measurement operators. Right? So as we learned just with the single systems, you can either just kind of write the wave function, then look at the coefficient, take the modulus squared and say that's probability. You can do it like that. Or you can do it a little bit more formally, which is that you apply measurement operators. So in this case, for each qubit, the measurement operator was, so for example here, MA would have been MA. So this would have been 2 measurement operators of S0, A on both of them. It's 1. So that would have been the measurement operator for MA, something similar for B. And then the combined measurement operator for both of them, because we're doing measurements on both of them, would just be the tensor product of both of these. So if we just do the first one, so MA, say 0 times MB 0 would be S0, 0, so that's the measurement operator for Alice. S1 is 1, measurement operator is for Bob. Or in my usual more compact notation here, where I just write it together, I just write it as S0, S1, S0, S1. So that would be, oh sorry, I think that what I just did there was actually the second one here. Yeah. And this is the special case of if the state itself was independent, right? So if the state was just like a product state, this was the case when they're totally independent from each other. Essentially what I'm trying to say here is that, well, if we just look at so even though it's like a 2-particle system, we're going to do a 2-particle measurement, actually because the underlying states are actually completely independent. So what we should do is we should recover the same result as we had before for the single qubit, because if they're completely independent, then you might as well, it should be no different to the single qubit case. So that's basically what I do here. So if I say what's the probability of getting that outcome of S0, well, in this composite system language, it would be the probability of getting that one and this one, and probability of that one and getting that one. So kind of combining the 2 probabilities there. And because of normalization, this recovers the same result. Well, this is a more, this is a more sort of formal, well, more general way of saying the same thing. So if I'm only making measurement on Alice, then actually the operator would be like this. And just if you follow this, you can show that it's the final state only achieved a measurement on Alice, and Bob's state is unchanged. So that's just the same. And basically that's the case if you don't have a measurement box here. You only have the measurement box Alice. Right, and then so I don't know. This looks like a lot of equations, but what I'm saying is actually nothing really too complicated. Again, just remember that when I write an observable, so general observable operator. So this is what the case was for a single system. So just have some values, and this is each outcome n, right? But now in a composite system, you've got like basically two variables because it's all different combinations, right? So the way that you generalize that is that basically like n becomes like two labels, so that now there's n and I call it NA and NB, right? NA and B. So there's two labels because everything is now labeled by I've written M. Okay. N becomes NA and B. So in other words, there's some. You have to put NA and B here. Everywhere you have N, you just replace by NA and B. Here, NA and B. And that's the observable operator for the composite system. And the wave function for the composite system, again, it's very similar. If you have a wave function in a single qubit, you just have this. But for a composite, the n just becomes NA and B. So for the composite system, it'll be NA and B. This has two labels, NA and B. This has two labels, NA and B. And then so if you write the expectation value, then it will, again, these are the probabilities, and these are the values. And for independent observables, so this observable here, A and B, so this could have been an arbitrary matrix, but for independent observables, it takes a more special form where it's this product form. So this was the case like in the Bell's inequalities case. This operator Z, ZA, ZB, for example, this was just a product. So the observables are actually independent. Of course, you can have some observable which is not just independent, more general than that. But again, this is just a more common case because this kind of thing would be achieved by doing measurements separately for each particle. Examples, and so this is actually a bit more like how we evaluated these things. Okay, for more than two parties, then you just keep on adding indices basically. Okay, does that clarify? Any other questions?
Actually, I have a lot of questions. I have maybe solve in 5 minutes.
Okay. Which one is most urgent?
The Deutsch's algorithm.
All right.
And the last one pages about
Okay, so Deutsch's algorithm. All right, so we're trying to evaluate either constant or balanced functions. Then we've got this oracle. We went over that bit, and this was the way that the oracle works. That eventually, it's going to be used. And then this is the full form of Deutsch's algorithm, and this is how it evaluates. It's probably the last slide there, right? So, right here.
So I have a question about the things in the orange box.
Yep.
So this is a conclusion that tells us that this operator only changes a sign,
Yep.
but they don't change anything else.
Yes.
The second page, I think
Yeah.
we just ignore the second qubit.
Yeah, well, we ignore it, or you could put it in there, but basically the whole thing would just be multiplied by this tensor product with minus. So maybe the way to think of it is that this is just a special case of this, or the operation of this oracle. So when the second qubit is, the input is a minus state on the bottom, then the way that this oracle acts is just in this way. So this is a particular case of what happens with the oracle. And because this minus never really does anything, kind of drop it afterwards. But you can equally put it there. It would just mean that, for example, here there'd be a minus, here there'd be a minus. Just put minus everywhere, minus state everywhere. Here there would be minus. So just sort of abbreviated. Just.
So in this example, we just apply the Hardeman gains on the first qubit, then we'll get a plus state.
Yeah.
So X is plus, right?
Yep. Well, yeah. Although I think what I mean by this notation here is here X is only really defined as 0 or 1.
Okay.
So when you have a different state, so it's not, maybe saying X is plus is a bit misleading. So perhaps I should write X is only 0 or 1 here. And then basically in quantum mechanics, everything is actually always linear, right? This is why we use linear algebra. So whenever we have an operator and then we have some superposition like this, you can always work out what the final result is by just looking at what happens on each term. So
So we just ignore the coefficient of the square root of 2.
Well, yeah, that I also just abbreviated because often you just sort of abbreviate the normalization because it doesn't do anything very interesting. So, yeah. Yeah, okay, so a lot of stuff is abbreviated, is maybe the answer to your question.
And about the charts, next page. So why is the output of oracle and the output of circular different?
Because of this extra that thing there. So okay, maybe I should have been a little bit more explicit. I said basically this is the state at this point, right? Yeah. before I apply the Hadamard, before I do the measurement. But after, say, here's the output. In this case, I apply Hadamard. Hadamard on this is a plus state. Hadamard on the plus state becomes 0.
So we just simply ignore the coefficient. Actually, if we added the coefficient, it's actually a plus state. So the output of the oracle is actually the plus state. And then we use the Hadamard again to flip into zero state.
Output of the oracle is plus state.
Okay.
Output of the oracle here is minus state. Here is also plus state up to some phase. Here is also minus state up to some phase.
Okay.
Yeah. And then you apply Hadamard, and then it becomes these states. And then you do a measurement in the 0-1 basis. And then, well, if it's 0, then you'll get 0 100% of the time. If it's 1, you get 1 100% of the time. So actually this works 100% of the time.
Yes, I think it's more easier to understand if we add the square root of 2.
Oh,
I mean,
okay.
we know that this is the plus state.
Alright, okay. I'll try and update the slides for next year.
And I also have questions about the growers and property.
Okay. Okay. Whereabouts? So this is similar to.
This is the definition of phase inversion.
Yeah.
So we just change the sign of the zero state.
Yeah. Yeah. And again, this x is only really defined for computational states. So x is only like 0, 0 or 0, 1 or 1, 0. It's never like a plus or something.
And then there is like a visualization of this phase inversion. So why is like just flip it about the axis?
So I guess it's sort of done by analogy, this argument. But so the first thing is to look at the oracle, right? So for the oracle, what we did was first write it in this new basis of solutions and not solutions. Right? So where's the definition here? Yeah. So we've got some function, or the oracle, which tells us which states are the solutions, which are not. Right? Gives a minus sign for the states that are the solutions. So what we're going to do is just define these two states such that this is the state, which is a superposition of all the states that are not a solution, and here's a state which is a superposition of all the states with a solution. So I don't know, maybe we can just do a 2-qubit example. So for x not sol, so for example, this could be for a 2-qubit example. You did grow it, right? Yeah. So I think you made 1, 1 as your solution state, right? So for a 2-qubit example, it would be defined like this. And then in this 2-dimensional space, now consider having a general superposition of these two states, right? So just anything. The action of the oracle would be to put a minus sign here. And so what this is our initial state, and these two are orthogonal states, right? It's easily to see because they've got no states in common. So that's why I draw them with like the orthogonal axes. So if this is our initial state, now the action of the oracle is to put a minus sign on these solution states. So I think you can see that it's going to be now reflected along this line, which is the not sol axis. And so in this case, the V operation is something very similar, so that in terms of the V naught box, so this is the V naught. V naught would be something like so let me write something like perpendicular 0 and the V sol. I have to make up notation here. Okay, so perhaps maybe I'll make it like analogous to the other one. So V0 not sol, V0 not sol and V sol in this case would be defined like 0, 0, and in this case all the states which are not 0, 0. So like 0, 1, 1, 0, 1, 1, right? And then, so that's V0. But actually what you do is not V0 itself, but V, which is the thing which is surrounded by Hadamard gates everywhere. So what this ends up being is, sorry, my board is pretty messy today. So the V not sol would actually be the what it does is to apply a so for the V0s, these are the states that will have a minus sign applied to it. For the V, it's basically the same thing, but it's rotated by this Hadamard operation. And because the Hadamard operation takes a 0 state to a plus state and a 1 state to a minus state, the V not sol states would be something like plus minus, minus plus, minus minus. And the V sol states would be just the state plus plus. And this is the state that you apply a minus 1 to. So it's basically the same thing, but you just look in the plus minus basis. Okay. And so what I've defined here as so here's the plus 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 state. That's exactly this thing which I was talking about. And this perpendicular thing, that's what I mean by this guy here. It's a state that's perpendicular to that. And so just with exactly the same argument as on the previous slide here. So if I draw my V sol, which is actually just plus plus, and the V not sol, which is actually equal to this perpendicular thing, then if I had well, okay, so this time let's start this way. So if I had a state which was A plus, sorry, A of, which way around do I have it? Yeah, perpendicular minus, say, B of the plus states. Because the action of this V operator is to apply a minus sign on this state. So basically this will flip it to this state, plus. So the action of this is exactly the same, just that the axis is on this plus state. And then now how do we combine these two figures? Well, the key point is that actually both of these states can be also written in terms of the this x and x sol and x not sol. So you can actually draw these two things, so this one and this one, on the same figure, because actually this plus state, this one here, this axis, turns out it's something which is actually quite close. Sorry, this one is actually something quite close, but not exactly the same as this one. And you can already see it here, because this state plus plus is actually this, right? 0, 0, 0, 1, 1, 0, 1, 1. So this plus state is nearly that, but not exactly. It's missing one of the states. So that's why I've drawn it so that it's actually kind of similar to this x not sol, but it's pointing slightly up because it contains a small fraction of this one, right? So this is the, sorry, this one. Yeah, so sorry, this one is very similar to this one. So actually, that one, sort of plus that one, up to some coefficient, is actually equal to this one. And so that's basically what I've written here. That's a more general formula for it. And this perpendicular thing is actually also should be similar. Okay, it's not. Yeah, it's not really clear at all. So this one and this one, I'm not sure how they're really similar, but well, certainly it should be sort of perpendicular to this one, right? And I think you should be able to do a calculation. I can't just see it by looking at the formula, but this perpendicular one, I think you can also write completely in this basis, and yeah, and I guess this overlap with this state and this state will be larger than the overlap with this one.
I see it. It's like during this operation, and rotates this vector bit by bit, and this get closer and closer to the solution.
Yep.
Got it.
Yep, that's right. Yeah. So it's like this double reflection. So it starts here along the green axis. This is where it initially starts. First oracle flip takes it there, and then because it's a reflection around the red one, and then the second one is now a rotation, a reflection around the green axis, and then so now it takes it up here. So after the first two steps here, it's actually got closer to the target, which is this blue one, red one, by an angle theta.
So we need to repeat it for like a certain number of times.
Exactly. Yeah.
And then we will get.
Exactly. Yes.
But that number is, we can actually calculate the number of the repeated time.
Yeah, you can if you know what well, basically this angle. So here's a formula for the angle. So m is the number of solutions, and n is the total dimension of the space. So if you've got something with, say, whatever, 10 qubits, then this n is going to be 2 to the power of 10. So this n will be the dimension of the number of qubits. And then, so yes, you can work out what the angle is if you know the dimension and if you know how many solutions there are.
I think you show it in the next page, which k is this.
Yeah, that's right. Yeah. Well, yeah.
So this is the least number of repeated.
That's right. Yeah.
process.
Yes. Yeah, so you can probably sort of see that you need to get this angle right, actually, because if you just keep on repeating, this will just keep on going around and around. Yeah. So you can actually do too many of these and then actually sort of overshoot and totally miss it.
Yeah, but this number is different from this one and this one. It says that we repeat or
Yeah.
so
Well, yeah, I'm just talking order of magnitude.
okay.
So, okay, I mean, pi over 4 is 0.7.
Because it may overshoot if we do too many times.
True, yes, that's right, yeah. Usually people are mainly concerned about, like, the scaling of this. That means, like, so when n gets very big, how many times, what is the number of times you need to repeat something in your algorithm? So normally people are not that concerned about any factors here, but because I was kind of making this derivation, I just kept the factor there.
But if we ignore the factor, it would probably be overshoot. And we've got.
Right, yeah. Yeah. Yeah, I suppose so, yes. Yeah. Yes, it would overshoot it. Yeah. Yes. That's correct.
Thank you.
Okay. I've gone over time, but I mean, I'm happy to answer any more questions if you don't have to be anyway.
No, I don't have any questions.
Okay. Okay, Danny?
I don't have any.
Okay. All right. Yeah. Okay. So the exam will be, kind of like the midterm, more or less extensions, similar to the homework questions, problem solving. So yeah, if you have any more questions, then you can let me know. But yeah, otherwise it was a pleasure teaching you. It was a fun class. So I have some awards. Some awards to give out for you guys. So here's an award for you, Danny, for 100% perfect with attendance. And here's your prize and one Kit Kat. And here's your award, Dylan, for best participation and attention. So yeah, so I hope you got something out of the class, and yeah, if you have any more questions or want to learn anything more about quantum, then feel free to come and talk to me. Okay. All right.
Just one more question.
Yeah.
Will we cover the density matrix in our exam?
Possibly, yes. But I know you didn't have any homework questions on it.
Yeah.
So I think I won't go too hard on you on the density matrix stuff. Yeah, because you didn't really get much practice with it. But yes, it might be there. Yes.
Yeah, but I think the slides.
Slides are not uploaded. The slides are they uploaded to NYU classes?
The density matrix part are not uploaded.
Okay. I'll upload that straight away then. Yeah. Okay. Okay. Great.